Hi, welcome back. Today we have a question which is a pressure drop of 700 kilopascal is measured over a 300 meter length of horizontal 100 millimeter diameter rough iron pipe that transports oil having the S equal to 0.9, the V kinematic viscosity 10 to the power of -5 meters squared per second. Calculate the flow rate using Moody diagram and B alternate method. Alright, the first step, we need to analyze the question. Calculate the flow rate. Alright, so in this case, the flow rate is Q. We need to find the flow rate. So in this case, when we solve the problem related to the loss in the pipe system, we look at this is under category number 2, which is the question asks the Q here. Alright, we need to find Q. They will give you the D. Alright, you can see the diameter 100, and then the E, the roughness element height, directly from this, okay, from this Moody diagram, you can get the E, rough iron here, you can get the E, and then here, the kinematic viscosity, you can get here, is given, and then the heat loss, right? The heat loss you need to find, alright, directly from this one, from the Moody diagram, you get the F, calculate the value of HL, and then finally you will get the flow rate. Alright, so let me start calculate the flow rate using the Moody diagram. Alright, so step number 1, in order to calculate the flow rate Q using the Moody diagram, we need to find the Reynolds number and relative roughness, as this will find the friction factor. Alright, so first we need to find the Reynolds number, or we need to find the relative roughness. So step number 1, we need to find friction factor first from Reynolds number and relative roughness. Okay, so step number 2, we need to find one by one. So we need to find E over D. So E over D, it is given that it is rough iron. Rough iron pipe, you can look at the Moody diagram. It is given already. Rough iron, let me highlight that. Rough iron. Okay. Rough iron having 0.046 millimeter. Okay. So from here, you substitute 0.046 millimeter divide with the pipe diameter, which is in this case 100 millimeter. Make sure the unit is consistent when you divide length with length. Alright, so you cancel out, you will get the answer to be 0.00046. This is relative roughness. And then we need to assume that since the velocity is not given, so it is difficult to get the Reynolds number. Now you can make assumption that the flow is completely turbulent flow. So when completely turbulent flow, definitely Reynolds number is infinity. It is very big Reynolds number. So step number 3, assumption. Since the velocity is not given, if we get the velocity, we can directly get the volume flow rate. However, this part is quite tricky. You need to make assumption first. The flow is completely turbulent. Assumption, flow completely turbulent. So when the flow completely turbulent, therefore the Reynolds number in this case is infinity. Alright, so look at the table or look at the diagram. This value and this value, this Reynolds number infinity refer to this one. Alright, this one is Reynolds number infinity. It's a very big number, so we choose the left. Sorry, we choose the right one. Okay. In this case, we can choose this one, Reynolds number infinity, and then our relative roughness to be 0.0000046. Okay, let's find out. So this one is Reynolds number infinity. We choose this line. Okay, this line refer to Reynolds number infinity. We take it the maximum one. Okay, we draw. Okay, you should use your ruler. Okay, this one just my handwriting. And find the relative roughness 0.00046. We have 30 and 46. This one. Okay. So around this range. Okay, you draw here a little bit top of this. Okay. So this one is what's the intersection? Definitely this region. This is, let me use the different color. Okay. This is the intersection point. When this is intersection, directly plot the plot to the horizontal axis. And then you will find that your friction factor, your assumption of friction factor to be in this range. Okay, so your friction factor here, your assumption first might be 0.0165. Okay, you can get 0.016. This is within this range. You can see here. This is 5, 6, 7, 8, 9, 10. Alright, so 0.016 around like that. Okay, you choose this number. Okay, you can put 0.016 also, should be no problem. Okay, so our friction factor based on our assumption completely turbulent. You can see here, completely turbulent region in this region. Alright, so your friction factor in this case, okay, refer Moody diagram, your friction factor to be 0.0165. Okay, so from this friction factor, okay, we can get the heat loss. Okay, we can get the heat loss. So this one under step number 4, we can get the heat loss, which is HL equal to F L over D V squared over 2G. Okay, so in this case, we still need to find the value of V, the velocity here. Alright, so how to get this V here? Okay, so since our heat loss, the formula of heat loss require the velocity, average velocity. So by using, okay, by using special formula, which is a Darcy-Weisbach, okay, equation, okay, which is V equal to 2G DHL over with FL, the power of 1 over 2. Alright, this method require you to get the HL. Alright, but this one you need to get the V and then you can get the HL. So we have the issue here. We need to find the V, but in order to get the V, we need to find the HL. So what you need to do here is that you can actually using the energy equation. I hope that you remember. Alright. So using step number 5, using energy equation. Alright, where remember that energy equation is work rate of the pump plus pressure 1 over gamma plus V1 squared over 2G plus Z1 equal to, alright, work rate of the turbine plus P2 over gamma plus V2 squared over 2G plus Z2 plus heat loss. Alright, so in this case, the pressure is the different. Yes, we have the variety of pressure along the pipe. So this is your pipe. Okay, this pressure point and this pressure point is different. And then there is no pump, cancel. There is no turbine, cancel. We can cancel out Z1 and Z2 as well. We have the heat loss. Okay, we have the friction, which is HL. And the velocity here, V1 here and V2 here is assumed to be the same or average because this is turbulent. The velocity is fluctuating. So we average them together. So V1 and V2 is the same. Because it is a fluctuating velocity, we average them. So that's why we use as average velocity throughout the pipe. So V1 and V2 we cancel out. So what we left here is P1 over gamma equal to P2 over gamma plus heat loss. Alright. Thus, we need to arrange this one, move to the other side. So, P1 minus P2 over gamma equal to heat loss. So, in other words, heat loss is equal to the change of pressure drop or the pressure drop over gamma. Okay, so we can get directly the heat loss. So, here, it is given the pressure drop 700 kilopascal. So definitely we can get the HL using the pressure drop. Okay, which is 700 kilopascal divided with gamma. Alright. However, the gamma here, it is given that this is not the water, it is transport oil. So your gamma here must multiply with 0.9. Alright, this is 0.9. So 0.9 multiplied with the gamma, which is 9810. Alright, so you will get your answer to be 79.4 meter heat loss. So from this heat loss, you can use the, okay, you can use this one. Okay, you can use the Darcy-Weisbach equation, which is V equal to 2G dHL over FL, the power of half. Alright, so using the Darcy-Weisbach equation, this is step number 6, using the Darcy-Weisbach equation, which is to get the velocity. I write it down, 2G dHL over FL, the power of 1 over 2. Just substitute the value, 2 multiplied with 9.81 multiplied with diameter of the pipe. It is given here, 100 millimeter shall be 0.01. 0.1 meter multiply with heat loss, which is 79.4, over with friction factor we discovered previously, 0.0165, multiply with total length of the pipe, 300. It is given the power of 1 over 2. So you will get 5.61 meter per second. Right? Alright, remember previously we made assumption that it is a fully turbulent flow. Since we have the velocity, why not we refine again the Reynolds number, the real exact Reynolds number, to get our solution accurately. Alright, so step number 7, if we have the velocity, why not we look at the Reynolds number and then we can translate into the friction factor. So recheck back our Reynolds number. Previously we assumed that Reynolds number is infinity. Now we need to recalculate the Reynolds number. Okay, our Reynolds number is Vd over nu. Okay, so from here, our velocity 5.61 multiplied with diameter 0.1 over with 10 the power of negative 5. This is given. The mu is given. The nu. Okay. So you will get the Reynolds number to be 5.61 the power of 10 the power of 4. Okay. And then again using the relative roughness, you calculate before to be 0.00046. By using this number and this number, look up the Moody diagram to get the real friction factor. Okay, so friction factor should be, okay, let's look at together. So here, Reynolds number you calculate previously to be new Reynolds number, okay, R new to be, okay, 5.6 multiply 61 multiply with 10 the power of 4, and then your relative roughness, this is still the same. Okay, using this value and this value. So we need to look up the 5.61, 10 the power of 4. Okay, so 10 the power of 4 in this region, in this one. Okay, 5. This is 1, 2, 3, 4, 5. Okay, this one. So using your ruler, directly plot. Okay, this one. Go straight. Okay. And then this one, you meet with this one. Okay. So this is your intersection point. Okay, this is your intersection point. So directly look up the value of F. Okay, and then you will realize that your F is actually, okay, your F is actually 0.023, because this is 2, 1, 2, 3. So your new F is 0.023. Okay. Your new F should be 0.023. Right? So from your new value of F, okay, you need to recalculate again the you can get directly the velocity, your new velocity, using the Darcy-Weber equation, which is 2 GDHL over with FL, because the head loss is the same, but the difference now is your F. Your V, your velocity, previously you use your the assumption one, your F assumption, which is 0.0165. Now you have found the correct value of F. So why not use your new velocity? Okay, so 2 multiply with 9.81 multiply with 0.1 diameter multiply with head loss. Okay, it is the same. 79.4 over with your new friction factor. This one. Okay, this is new, yeah. Like, make it new. 0.023 multiply with the total length of the pipe, 300. This is third, or the power of 2. You will find your new velocity to be, this is new, 4.75 meter per second. Thus, with your new discovered velocity, you can get the volume flow rate, which is Q equal to AV. Area, which is pi r squared, which is radius, diameter is 0.1 over 2 squared. Multiply with velocity 4.75. So the final answer should be 0.037 meter cubic per second. Alright, that is the final answer using the Moody chart. However, the question asks two methods for the second one, which is alternate method. So again, in the alternate method, you can directly plug in the value. So step number 10, using alternate method, which is under Q equal to negative 0. Okay, this one you can look at the formula. This is a generalized formula. 0.965 G D5 the power of HL over length, total length, the power of half, okay, ln the bracket roughness over 3.7 diameter plus bracket 3.17 V. This is the dynamic viscosity squared L over with GD, the power of 3 HL. Okay, this is quite lengthy, 0.5. Okay, this is for Reynolds number more than 2000. Okay, now our Reynolds number is definitely more than 2000. Alright, so just substitute the value here. Alright, so negative 0.965 multiply with gravity 9.81 multiply with diameter 0.1, the power of 5, the heat loss 79.4 over with 300. Okay, the length of pipe, the power of 0.5. You learn this one, you need to solve inside, which is this one is referred to the relative roughness. So just substitute here 0.00046 over 3.7 plus 3.17. Okay, 3.17 multiply with the kinematic viscosity. It is given here 10 to the power of negative 5. Okay. Okay, 10 power of negative 5 Let's square it. Okay, this is a power of 2. And then multiply with the total length, which is 300 over width, gravity 9.81, diameter 0.1 cubic, multiply with HL. Okay, HL is 79.4, the power of 0.5, close bracket. So using your calculator, you will find that your answer, this one you simplify, negative 0.965. And then this one you solve, you will get 5.096, the power of 10, the power of negative 3. Multiply with this one, you solve, negative 7.655. Okay, and then the final is 0.038 meter cubic per second. Now you see the solution. It is almost the same with the using the Moody diagram. Moody diagram is 37 with the alternate method 38. I think that's all about the solution. Thank you very much.